So this lecture is going to cover section 5.2, which is connectives and their Venn diagrams. So let's start with complementation. If set A is drawn from some universe U, then the complement of A, symbolized as A prime. So this little, let me just get my pen. So this little mark after the A is called prime, or we could say a complement. It's the same thing, but that symbol's a prime symbol. So that would be the set of all elements that are not in A, but still in the universe. So for example, why does it always do this every time I go to highlight for the first time? Why is this doing this? Okay, we're not going to do that. We're just going to draw. So for example, let the universal set be U, which is 1 through 10, and A is 1, 2, 4, 7, and 8. Then what's A complement or A prime? So that would be all of the elements that are not in A, but that are in the universe. So that's going to be, so 1, 2, 4, 7, and 8 are in A, right? So everything else in the universe would be A complement or not in A. So that's going to be 3, 5, 6, 9, and 10. We could also draw a Venn diagram that would represent this relationship. So let's say this is the universe, and then we have set A. So in set A is 1, 2, 4, 7, and 8. And then everything not in A would be 3, 5, 6, 9, and 10. So that would be A complement or A prime. So let's talk about membership tables. A membership table, think of it, it's analogous to a truth table in logic. So remember in a truth table, if we had two simple statements, right? Like P and Q, we could set up our truth table, right? At first, whether it was for a disjunction or a conjunction or a conditional, whatever the case may be. This is using a membership table for these different connectives. The first one's going to be complementation. It's a way to show that an element is or is not a member of a set. So for example, the membership table for complementation is shown down here. So this is what we could do. So remember when we were listing like our true false values, right? For some letter, whether it's P or Q or whatever. So either, think of it now, we're going to use our element symbol. So it's like either something's an element of A, right? Or it's not. An element of A. I'm sorry, this is just glitching a little bit. It's going a little slow. So if we have a complement in the next column, then if something's an element of A, then it's not going to be an element of A complement, right? Or A prime. And if something's not an element of A, then it will be an element of A prime or A complement. So which truth table does this remind you of? This was similar to the negation truth table, right? Remember in negation, if we had P and let's say not P. So P could be true or false, but if P was true, then not P was false. And if P was false, then not P would be true. Very similar, right? So let's talk about the intersection of two sets. If two sets A and B are drawn from some universe U, then the intersection of A and B, denoted by A intersection B, so it looks like an upside down U is the symbol for intersection. That's going to be the set of all elements that are in both sets A and B. So in other words, what they have in common. So whenever we're looking for the intersection of two sets, think about where they overlap, where they have the same elements. So for example, here's my universal set 1 through 10. A is 1, 2, 4, 7, 8. B is 1, 4, 5, 6, 8, 9. What is A intersection B? That's what I want to know. So what do they have in common, in other words? So they both have a 1, they both have a 4, and they both have an 8 in common. So the set 1, 4, 8 would be the intersection of sets A and B. So think what they have in common, both. And we could draw a Venn diagram to represent that relationship. So here, let's say this is the universal set. Now A and B are going to overlap right where the intersection is. So let's draw two circles that overlap. So here is set A, here is set B. Now where they overlap, that's going to be the intersection, right? So in the intersection, and the overlap is going to go 1, 4, and 8. And then now A only has 2 and 7 left, right? So it's 1, 2, 4, 7, and 8, but A only has 2 and 7. And B has 5, 6, and 9, right? They only share the 1, the 4, and the 8. So B only has 5, 6, and 7. And then now, is there anything left, right, that's in the universal set that's not part of set A or set B? And that's going to be 3, right? 3 is in neither of those sets, or 10. So that's how we can represent this relationship using a Venn diagram. We can also create a membership table for complementation, very similar to our truth tables, right? So remember, whenever we had a simple statement, we would say true, true, false, false. So now we're going to assume, okay, element of, and then not an element of. And then for the other simple statement, we'll alternate. Instead of true, false, we'll do an element of, not an element of, an element of, and not an element of. So let's think about, now we have A intersection B, or both A and B. And I just realized that this was not supposed to be complementation. This was supposed to be, there's just a typo here. This should be intersection instead of complementation. So just change that. I just realized there's a typo. So membership table for intersection. So if we have something that's an element of A, an element of B, right, then it's going to be in the intersection. It's going to be an element of A and B. But if we have an element of A, but something that's not an element of B, it's not going to be in the intersection, right? It's not going to be an element of the intersection. Or if something's not an element of set A, but is an element of set B, it's still not going to be in the intersection, right? Because it's only in one, not both. It has to be both. And then if you have neither, right, not an element of A or an element of B, it's not going to be an element of the intersection. And this is similar to the truth table for conjunction. So now let's talk about disjoint sets. So if two sets do not share any elements in common, they're said to be disjoint. So they have no intersection. Their intersection would be the null or the empty set. So for example, we have the universal set is 1 to 10. Set C is 1, 3, 5, 7, 9. Set D is 2, 4, 6, 8, 10. Let's draw a Venn diagram to represent the relationship between set C and D. So here's my universe. And notice they have nothing in common. They're disjoint, right? C is 1, 3, 5, 7, 9. D contains 2, 4, 6, 8, 10. So there is no overlap. So I'm not going to draw intersecting circles. So we have set C, set D. Set C contains 1, 3, 5, 7, 9. And set D, so that's set C, set D contains 2, 4, 6, 8, 10. And the universe is already taken care of, right? Because we have 2, 4, 6, 8, 10, which is the even numbers in set D, 1, 3, 5, 7, 9, which are the odd numbers. And the universe is the numbers 1 through 10. So they're all accounted for. So let's talk about union. The union of two sets, think of it as the joining of two sets. So if two sets A and B are drawn from some universe U, then the union of A and B, denoted as A union B, so now it looks like a big U that's going to join the two sets, is the set of all elements that are in either set A or in set B or both. So we're joining the two sets together. So for example, if my universal set is 1 through 10, set A is 1, 2, 4, 7, 8. Set B is 1, 3, 6, 9, and 10. Let's find A union B. So in other words, we're going to join the two sets together. So we're just going to include everything between the two sets, right? So both sets A and B have 1. A has 2. B has 3. A has 4. B has 6. A has 7 and 8, and B has 9 and 10. So notice all I did was join the two sets together. That's the union of two sets. So if we want to represent this using a picture or a Venn diagram, if I draw my two sets A and B, they are overlapping, right? Because they both have a 1 in common. You see how they both share a 1. So that's going to be where they overlap or have an intersection. And then set A has 2, 4, 7, and 8. And set B has 3, 6, 9, and 10. So together, if you look at both A and B, that's the union of the two sets, and it includes what we listed right here between the two circles. Now to finish the Venn diagram, so notice how 5 isn't included in either set, but it's in the universal set. So 5 is going to go in the universe. So let's look at the membership table for the union of two sets A and B. So we have element of, not an element of, not an element of, and then element of, not an element of, not an element of. So now let's think A or B. So if we have an element of A or we have an element of B, the element's going to be in the union because it has to be just in one, the other, or both. So if an element is part of set A, but there's not an element, It's not an element of B. Even when we join the two sets, it's still going to be an element of A union B. If something's not an element of A, but is an element of B, and we join the two sets together, it is going to be an element in the union. The only time it's not, if it's neither an element of A or B, right? So when I go to join the sets A or B, it's not going to be an element at all because it's not an element of either set. So this reminds us of the truth table for a disjunction in logic. I just want to point that out just because it's relatable. So now let's talk about the difference of sets or set difference. So if sets A and B are drawn from some universe U, then the set difference, denoted by A minus B, is the set of all elements that are in set A, but not in set B. So for example, let's say the universe is 1 through 10. We have set A here, we have set B here. First, let's draw, I think it's easier to explain this first when we look at a Venn diagram. So let's construct a Venn diagram for this relationship. So here's my universe. Here's A. Here's B. So now let's start with the intersection. Where do they overlap? So what do they have in common? So sets A and B have 3, 6, 7, 9, and 10, right? So they have the elements 3, 6, 7, 9, and 10 in common. So 3, 6, 7, 9, and 10 would go in the intersection. Now, what's only in set A, right? That's not in both. So that's going to be 1 and 4, right? The 1 and the 4. And then what's only in set B that's not in the intersection? So that would be 2 and 5. And now what's in neither A or B, right? Because that'll be what's left in the universe. And it seems to just be 8. 8 is the only one that's not in either. Okay, so now let's find set A, the difference of set A and B, or A minus B, right? So it's going to be everything that's in A, but not in set B. So the easiest way to do this is when you're looking at the Venn diagram is look at A, right? It contains 1, 4, 3, 6, 7, 9, 10. But B also has 3, 6, 7, 9, 10. So take that away. The only thing that's left is just 1 and 4. So all the elements in A, but not in set B. So take away everything that's in set B. And then if we go the other way around, find set B minus set A, so the difference between B and A. Now, what are all the elements in B, but that are not in A? So look at the circle for B. B contains 2, 3, 5, 6, 7, 9, 10. But A contains 3, 6, 7, 9, 10. So take that away. We're only left with 2 and 5 in that set. And we could also look at the membership table for set difference. So specifically set A minus set B. So if we set up an element of, not an element of, not an element of, element of, not an element of, element of, not an element of. This is just glitching my pen. Hold on 1 second. There we go. Okay. So now let's look at the set difference. So if something's an element in A and it's both an element of B, if we take the difference, then it's not going to be an element of the different set or the set difference. If it's in element A, if an element is in set A and not in set B, and we take the set difference, then we're going to have an element of A minus B. And if something's not an element of A, but it is an element of B, then when we look at the difference, it's not going to be an element. And then if it's not an element in A, not an element of B, then it's not going to be an element in the set difference. So that's what the membership table would look like for the set difference. And what I did here was I just summarized what's in the book. So now that we've finished section 5.1 and 5.2, there's a lot of new symbols and definitions. So this is a nice little table that summarizes, and this is in the book, and I'm also going to post it separately in the module. So this way you could refer to it as a single sheet. Okay, so this is just a list of all different notation and definitions. So just a summary of set theory notation. So now what I want to do is let's practice. So now let's answer some questions, just to make sure we have the hang of this. So let's find, for the first one, let's find the elements in each set, given that we have the following sets. So we're starting with the universe. It's 1, 2, 3, 4, 5, 6, 7, and then we have sets A, B, C, and D. So let's find the following. So B prime or B complement, right? This is going to be anything that's not in set B. So if set B is 2, 4, and 6, it's going to be everything else, right? So it's just going to be everything else that's in the universal set. So B complement or B prime is going to be 1, 3, 5, and 7, right? That's everything that's not in B. Similarly, let me make this a little bit bigger. Let's find D prime or D complement, anything that's not in set D. So set D contains 2, 3, 4. So it's going to be everything else in the universal set. So it's going to be 1, 5, 6, and 7. So now let's find the set C intersection D. Remember, the upside down U looking symbol is intersection, meaning both. What is both in set C and set D? So C and D, what do they have in common? They just have 2. So that would be the intersection of C and D, the set that just contains 2. So now let's look at the set difference for D and C. So D minus C. So look at D, and anything that overlaps that's in C, we could get rid of. So you see how D has 2, C also has 2, but then D also has 3 and 4, but C doesn't contain 3 and 4. So the only thing that we're left with is 3 and 4. So that would be the difference between set D and C, that set that contains 3 and 4. Now, if I wanted to look at the difference between sets D and B, which is the next one, we have 2 is in D and it's also in B. And then 4 also could get taken away. So the only thing left in D is D minus B is just 3. So that would be the result. So the next one is A and B union C. So what's grouped together we have to do first. So let's off to the side over here, find A intersection B. So where do A and B overlap? So A and B share nothing, right? A is 1, 3, 5, 7, B is 2, 4, 6. So A and B is just the empty set. And we want to join that with set C. So we're just joining the two together. So an empty set joined with C in this case is just going to be C, because we're not joining anything with it because it's an empty set. So it's just going to be C, which is 1, 2, 5, and 6. So the next one is C union A, but complement. You see how we have the prime on the outside? And then we're going to take the set difference with D. Let's just go one step at a time. Let's start with C union A. So let's join sets C and A. So that's going to be 1, 2, 3, 5, 6, 7. I'm just joining the two sets together. But we want to take the complement. So we want C union A prime or complement. So it's everything else that's in the universal set that's not in this set. So that's going to be 4. 4 is the only thing that's not in the universal set. That's in the universal set, right? That's not in that union. So now we want to take C union A complement, which is 4, and then take away D. So we have set 4 minus set D, which is 2, 3, 4. So the 4 is gone, right? And now there's nothing left in that set. So it's just going to be the empty set. Let's look at the next one. We have A intersection C union A intersection D. So let's do the two intersections first, and then we'll join them. So A intersection C is going to be 1 and 5, right? Because they only contain those two. Intersection means both. So A and C have both 1 and 5. Now let's find A intersection D. So A and D have a 3 in common. So that's going to be that intersection. And now we want to join or take the union of these two sets. So let's join these two sets. Join 1 and 5 with 3. So it's going to be 1, 3, and 5 when I take the union of those two sets. So the next one is the set difference between A and B and then intersection C. So let's just do A minus B first. So A, we have 1, 3, 5, 7. B, we have 2, 4, 6. So the difference, B doesn't have anything from A. So think about there's like nothing to take away. So it's just going to be the set 1, 3, 5, 7. And now we want to join that with set C. and set C is 1, 2, 5, and 6. So we have to find the intersection. So what does set C and this set difference both have in common? So 1, 2, 5, and 6, and 1, 3, 5, and 7. So they have a 1 and a 5 in common. So the intersection is going to be 1 and 5. And then we'll do one more. So we have B union C minus, or set difference, B and C, but then we want to take the complement of that whole thing because you see the prime on the outside. So let's do one step at a time. Let's find B union C. So if I join sets B and C, I'm going to get 1, 2, 4, 5, 6. And now if I take the intersection of B and C, where do they have common elements? Just 2 and 6, right? So the intersection is going to be 2 and 6. Now we want to take the difference. So we have 2 is gone, 6 is gone. So the difference is going to be 1, 4, 5. But we want the complement of that. We want whatever's not in that set that's in the universal set. And the universal set is 1, 2, 3, 4, 5, 6, 7. It's 1 through 7. So the complement of this is going to be 2, 3, 6, and 7. So the answer to this is going to be the set 2, 3, 6, and 7. So hopefully this is getting you a little bit more comfortable with using, these definitions and notation. So this was a good example. Now let's look at example 2. Consider the following set. So we have the universal set here, and we have sets M and N. Let's construct a Venn diagram that's going to satisfy this relationship. So start with your rectangle, label it as the universal set. And we have two sets, M and N, that do have overlap. So I'm going to draw 2 circles, M and set N. And let's start with the overlap. What do M and N have in common? They have 15 and they have 25. So 15 and 25 is going to go in the overlap, in the intersection. Now, what only pertains to M then? Well, it's going to be everything else. The 5, the 30, and the 40. And then what only pertains to N? And that's going to be the 10, the 20, and the 45. Now what doesn't pertain to either, right? What's in the universal set that's not in M or N that we still have to account for? So we still have to account for, so we already counted for 5, 10, 15, 20, 25, 30, but we didn't account for 35. We accounted for 40, 45, and not 50. So 35 and 50 still need to be added to the universe. So this way we include everything. So that would be the Venn diagram that represents those sets. And let's just do one more example where we have to answer some questions regarding a Venn diagram. So here's a Venn diagram. It's representing the universal set and sets P and M. So find the elements in each of the following sets. So what's in the universal set? So that's just going to be everything. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it seems to be all the numbers from 1 to 12 that make up this universal set. Now, what is set M? So what's in M? So that's going to be 1, 2, 4, 6, 8, 10. Now, what's M complement or M prime? What's not in M? Well, that's going to be everything else in the universal set, right? So that's going to be whatever is only in P and in the universe. So that's going to be 3, 9, or actually we'll go in order. So it's going to be 3, 5, 7, 9, 11, and 12. What is the set difference between M and P? Well, if we look at M, which I circled in blue, just use the Venn diagram. And if I circle P in red, what's only in M, right? That's not in P. So if we take away everything in P from M, we're just going to be left with 2, 4, 8, and 10. And if we go the other way around, if we look at the set difference between P and M, now look at P, which is the red, but take away any overlap in M, right? So now we're just going to have 3, 9, and 12 in that difference. So the next question is, what's the intersection of set P and set M? So it's going to be where they overlap, right? So that's going to be 1 and 6. Now we want to list set P. So what's in P? So P is this, everything in this circle, right? So it's going to be 1, 3, 6, 9, and 12. And now what's not in P? What's P complement? Well, it's going to be everything else that's not in P. So whatever is left in only M and the universe. So that's going to be 2, 4, 5, 7, 8, 10, 11. Now, what's only in set M? So only set M is going to be 2, 4, 8, and 10. And only in set P is going to be 3, 9, and 12. And that wraps up the examples that I have for section 5.2. So I feel like I tried to do a variety. This way, we can explore and work with all the different, types of sets, whether it's a union, a disjunction, whether it's an intersection where we have to join, not join both, but the intersections where they both overlap, if it's the difference of two sets, if it's a complement. So I feel like I gave, a variety of different examples. So you should be okay for the homework. And then in the next lecture, we will start section 5.3.